It's a great pleasure to introduce Maud Vinet. She's a technology manager from here, CEA Leti in Grenoble, and she's in charge of the advanced CMOS laboratory. She has been working since several years on improving the MOS transistors' performances together with scaling dimensions. And during her career, she has worked on device design and the performance improvement of many types of devices. She owns more than 40 patents, and her team in Leti, Grenoble, has demonstrated the first CMOS silicon-based spin qubit. So she's now working in the development of this technology towards scalable realizations and merging industrial CMOS technology with state-of-the-art capabilities of the silicon CMOS technology and quantum nanoelectronics. So we are very happy to have you here, and please.
Thank you. Moi, j'aime bien comme ça. Et ça marche? Alors, je sais pas. Elle est où la mienne? Bah oui, je l'ai mise tout à l'heure avec le gars. Well, good afternoon. First, thank you very much to the organizers for providing me and us, in the name of the team, the opportunity to present you the work that is done in Grenoble towards a scalable silicon quantum, towards building a silicon quantum computer. All the work that I will talk about today is done in collaboration between CEA-Leti, which is the technological part of CEA, INAC, which is the fundamental part of CEA, which belongs to the fundamental research part of CEA, and this Institut NEL, which belongs to CNRS, and is also on fundamental research, and we belong to the University of Grenoble-Alpes. Just to set up the stage, we are at the fourth day of the conference, so I'm not going to remind you what quantum computing is looking after, but just to tell you what we are aiming at. So basically, we're trying to build a quantum computer that's going to be better than supercalculators, and meaning that to do that, and as belonging to a technological organization which has a high-performance computing roadmap, we are pretty much aware of the fact of what's going on in high-performance computing. So what we want to build, what we want to design is an object that's going to get hundreds of qubits and to perform millions of errorless quantum operations to overcome, to beat supercalculators. Millions of errorless quantum operations. We all know that no physical systems is currently able to reach this precision. So our assumption is that we will need quantum error correction protocols to cure from the defects. And these quantum error correction protocols come with a cost, which is an overhead in terms of qubits. So the object that we're trying to build consists in millions of physical qubits which are arranged in a 2D array. And in this 2D array, we will need to implement 1 qubit gate, 2 qubit gates, and to have a readout for each of these gates. So this is the specification towards the object that we are looking at. So when we're looking at this object, there are a couple of figures of merits that become of prime importance, and as an engineer, we are really looking at figure of merits to put the system together, and speed becomes of pretty much importance because it's the figure of merit that's going to provide competitive runtime for quantum calculation as compared to the current supercalculators. Fidelity is, of course, of prime importance to go above the quantum error correction threshold and to provide logical qubits that are better than physical qubits. And the size of the qubits is of importance from an engineering perspective, because if we want to put millions of qubits, we want to keep the size of the circuit manageable. So having that in mind, as an engineer, we try to put scorecards and to compare the state of the art and where the trends for each systems. Of course, it's biased from an engineering perspective because it belongs to our community. And the idea is that from a physics perspective, all these systems are very interesting. But when we want to put together all the properties, we really have to do trade-off. And when we look at the size, the fidelity, the speed, the manufacturing, the variability, and the variability is going to be of prime importance now, because if we have millions of objects on the same circuits, if we need to tune the properties of each subject, that's not going to be manageable at the level of the circuit. So we are really paying attention to the variability of the silicon, of the qubits. So when we look at all these figures of merit, we see that the silicon spin qubits are very promising. The size of the circuits is in the 100 nanometers square. Fidelity in 2 qubit gates is around 98%. And we know that there is some order of magnitude to win, and we will look at the data on how to do that. The speed is kind of reasonable, and to go to millions of operations, we will be in the second range, which is okay in terms of calculation. And the first numbers of variability are very encouraging. What is striking is that the number of entangled qubits is kind of lagging behind as compared to the other systems, mostly because so far all the qubits have been demonstrated in lab environment. And this is where we believe silicon has another opportunity, is that a few silicon qubits have already been demonstrated in lab environment. And what we want to do is to leverage the maturity of the semiconductor industry, which routinely builds circuits with billions of transistors. We want to leverage this maturity to overcome the challenges of variability and large-scale control to design this fault-tolerant quantum processor. And this is really the philosophy in which we're trying to build our large-scale quantum computer. There have been several quantum architectures that have been proposed in several groups in the world. This architecture proposed by QTech in Levens van der Zijpen's group relies on small quantum cores which are interconnected by long distance quantum links, and all the quantum electronics is located in between these small quantum cores. This architecture was proposed by UNSW and relies on very tight integration of transistor on top of each qubit to allow for a tuning of each qubit individually, which sets up very strong constraint on the dimension of the technology to be used, and some more refined architecture allows in between these two architectures to decrease the number of control, still having some ways to tune individually the qubits. So in Grenoble, what I will tell you about is the fourth architecture, and I will try to detail you all the steps that we are taking towards having a quantum computer. So first, we need to have good qubits. Then we need to put them in an array. Then we are setting up long-distance quantum information transfer to overcome some size limitation of the array. And we have to take into account all the constraint to design an architecture which is compatible with the cryogenic constraint. So first, looking at the single qubit level, first thing, silicon spin qubit rely on the manipulation of the spin of a single charge electrically confined in a quantum dot. So first we need to learn how to build quantum dots, and this is what we've been doing since the story began in '96. So since a few years, we're trying to have clean quantum dots where we can confine electrons. So we began with large numbers of electrons, and as we improve our understanding, we're now able to confine one single charge, whether whole or electrons, in a quantum dot. And basically what we rely on is a standard, mostly standard CMOS geometry, where the quantum dot doesn't really work. The quantum dot is located under the gate of a transistor. We have made slight changes to the standard CMOS technology. Then having this charge which is trapped in a quantum dot, we need to manipulate the spin of this charge. And this is what we have done. In 2016, we have demonstrated the first silicon spin qubit in a CMOS technology. It was a whole qubit, and basically what we manipulated was the spin of an electron which is located under gate 1, and we used Pauli spin blockade with a spin located under gate 2, which act as a filter, and we measured the current that was flowing from source to drain to know the spin state of that was located under gate 1. So we got started with whole spin qubit, which are thank you. Which are interested because they can be easily electrically manipulated. And later on, we demonstrated that we can also design electron spin qubit controlled by an electric field. And you've seen a presentation on this topic yesterday. Now, that's being said, so we've got one electron and one whole qubit. What we need to do is to have high fidelity readout that is compatible with large-scale quantum computing. We cannot use the spin filter that we were using earlier. So basically, what we have developed is RF get reflectometry in order to have a readout that becomes compatible with large-scale integration by the use of tank circuits that allow for a frequency multiplexing for each of the qubits. And with this technique, we've been able to demonstrate fidelities, readout fidelities above 99% at a speed of 500 microseconds, and now we're working on decreasing the duration of the measurement. So what is very interesting in silicon is that it can be not only it benefits from the maturity of the semiconductor industry, but the material in itself can be engineered in order to have a very low noise environment because we can purify silicon and just use 28 silicon isotope in order to have a spin vacuum. And this isotopic purification leads to the suppression of the dephasing induced by the 29 silicon nuclear spins. And you see the number of operations per error as a function of the time, and you see that most of the gain has been realized thanks to the introduction of silicon 28 with a threshold above 1,000 reached by the Riken group in silicon 28. And what we have done very recently is that we have installed a 28 silicon supply chain in the clean room to be able to fabricate 300 millimeter wafers in silicon 28 to be able to process these wafers in the standard CMOS technology. And they are compatible with the microelectronic requirements. So just to summarize what has been done in terms of the definition of single and few qubits, the learning, we've been using CMOS geometry to define the quantum dots, to know how to define the quantum dots. Within these quantum dots, we have learned to isolate one single charge in the dot. We have demonstrated that we are able to control the spin of this single charge and define whole or electron silicon spin qubits. And we've been working on the single shot readout techniques in order to design and optimize some scalable readout techniques. Now what's going to come next is the quantification of the impact of the material improvement. So we're designing the same samples in 28 silicon, and we're designing several quantum dots in series to be able to design linear arrays of qubits. Now, that's one step, how to improve the single and few qubits quality. And this CMOS baseline is really used to get some learning in the material and in the technology. In parallel, we are thinking of how to design the array. What's going to be the 2D geometry? And first question is, so in an array, what we want is qubits or quantum dots that are interconnected to each other. So there are two questions, at least to be answered, is what is the size of the quantum dot and which distance should they be from one another. So first question that we have begun to address is the size and the distance between the dots. And to do so, what we have done is that we've used our existing quantum dots, and we have checked whether how we're able to have the quantum dots that is defined thanks to the lithographic dimensions that are used on the wafer. And to do that, we have compared the charging energy, and the charging energy relates to the dimension of the dots. So it is a probe to have access to the quality of the fabrication. And what we've measured is that with charging energy, which is around 8 milli-electron volt, which tells us that the size of the dot that we are looking at is around 20 nanometer, which is in the range of the dimension of the dots that we are fabricating. And so the first learning that we have is that the size of our dots is defined by the lithographic dimensions and not by the intrinsic disorder on the wafer. So that's a first information, and the second information is that 20 nanometer is a dimension that is routinely used in the semiconductor industry, so we can use standard lithographic techniques. So this is the first step to tell us that we have some knobs to tune, to design with the current tools that we're using. So that's on one side, on the silicon quantum dots. And what we are doing on the other hand is that we are leveraging the knowledge that is generated in 3-5 semiconductors. So the 3-5 semiconductors are easier in a first step to manipulate because they intrinsically can be designed to have a two-dimensional electron gas. So there are already charges in the system, and we have used this two-dimensional electron gas to design an array of quantum dots. In this case, this is 9 quantum dots, and we have been able to have access to the charge state. So we've been able to put one charge in each of these dots, and this graph shows you the charge state for one electron that goes from the top dot to the top right dot, and we can move this electron in this array. Now we've been to the next step where we're trying to load one electron in each of the quantum dot, and the charge state is now much more complicated because we can have several configurations. But basically, we compare the simulation with the experiment, and what we are able to know where our electrons, which is, and this state, for instance, correspond to this configuration of the 5 electrons that are in the state. And now we are using this 3-5 array to have some probe on how to load and how to control the charges in a bigger array. And going one step further, we have now loaded electrons and charges in a 2D array, and we are now manipulating the spin of two adjacent charges in an array to start doing quantum manipulation inside a 2D array. And these are the first coherent oscillations of two electron spins within a 2D array. So to summarize into the array definition, we have two paths currently. One which is in silicon, where we're looking at which dimension to use, and now we have demonstrated that the range of 20 nanometer sounds appropriate to get started with state-of-the-art materials. And on the other hand, we are leveraging the 3-5 materials as a test bed for procedure settlement. So first to load one electron in each quantum dot, and then to coherently manipulate spins in any of the two adjacent dots in the array. Now, we don't know which are going to be the limitations in terms of size of the array. So we need to plan for a long distance transfer of the quantum information. So we are also leveraging the 3-5 platform to set up long distance coherent link, and we have been able, thanks to a surface acoustic wave, to demonstrate a coherent transfer of information over 6 micron. So this is the first demonstration of long distance coherent transfer of information in solid state, and we are now looking at how to transfer it to silicon where there is no surface acoustic wave. Now we want to put that in a whole package, and we want to design an architecture that's going to be compatible with all the system requirements. So with what we have currently, so we've seen that we've got we've got 1 qubit, we've got a 2D array in 3-5, and the question is how to put a large-scale quantum computer all together where the qubits are going to sit next to each other, and we want the qubit to be able to be 1 qubit gate, 2 qubit gates, and to have the readout in each qubit. And we've seen that currently the readouts that we've been using, the sensor and the qubits are at the same level, so we are stuck with a topology issue where we can't have all the qubits communicate to each other because we have this sensor in between. So the idea that we're trying to leverage is now to leverage the third dimension, so that we have the readout of the qubit that is located beneath the qubits, and then leveraging the large-scale technique, very large-scale integration techniques, we can design an array of qubits. And this is what it looks like. And just to comment a little bit on the architecture that we are working on, we have a set of control gates on top of the qubit layer, which we're going to use to tune the coupling between the between the qubits to design 1 and 2 qubit gates, and so to control and design the coupling. And we're going to have an array of a sensing layer located beneath the qubits that we're going to use to perform the readout of the qubits. Now the question is how to design those layers, and what we are there is a question which is how to tune the coupling between dots, and this question is used at the same time to design 2 qubit gates or to design to relate the qubit to its sensor. And what we are leveraging is the knowledge that we have generated in the standard CMOS geometry plus the 3D technology. And what we have seen is that we can actually tune by playing on the electrostatic configuration of adjacent quantum dots. We're able to tune the tunnel rate between adjacent quantum dots on 6 order of magnitudes. And this is doable when we have a distance between the quantum dots between 30 and 100 nanometer. So we're using this 2D knowledge now to design our first matrix of quantum dots and of qubits. That's one question. Second question is how to control those qubits. So we were saying earlier that there are some geometries where we need an individual control for each of the qubits. When we're talking about millions of qubits, it means that we need millions of individual control, which is not scalable. So what we want to do is to reduce the number of gates as proportionally to the square root of the number of qubits. And to do that, we're going to use a line and column addressing architecture. And you've got a moving picture of how the potentials are going to behave in this architecture. And we're going to use frequency multiplexing. So it relates to what I was telling you earlier, that we are designing RF gate reflectometry in order to be able to implement this frequency multiplexing. So thanks to that, we want to design this large-scale quantum computing. Now looking at what it means when we have 10, if we want to go to, what it means for a million of qubits, we need a terabyte sample per second in terms of data transfer. And this is the number of data transfer that are currently targeted by 5G technologies. So we are leveraging a lot of the technologies that have been developed in the mainstream of the microelectronics roadmap. To finish, just a few words on the control electronics and which technology we are going to. So to build a quantum computer, we are going to have the quantum core, and we've got the quantum, the control electronics that is located around. And this control electronics is going to obviously dissipate some power, and we are at low temperature. So we want this power to be as low as possible so that the addressing architecture can actually address all the arrays of the qubit, and that it's not limiting in terms of qubits. And basically, the power that is dissipated in electronic circuits depend on the activity. Well, it means when the transistors switch on and off, the number of transistors, their frequency of operation, the load that they are charging, and the supplied voltage. And we want the supplied voltage to be as low as possible. And to do that, we're trying to leverage a Grenoble specialty, which is the FD-SOI technology, and which is a technology, a transistor technology, which has a unique fourth electrode, which allows to in situ tune the threshold voltage of the transistors, and as a consequence, we can lower down the threshold voltage of the transistor, which is going to allow us to lower the supplied voltage. So what we are now at in terms of dimensioning is that we have up to 20,000 Morse at full activity to help us doing the control electronics, and we are on the other side working on increasing the temperature of operations of our qubits so that we can go even further in terms of control electronics to be able to address the whole array of qubits. And finally, the way we're going to put together the control electronics and the quantum core is going to be by leveraging the 3D technologies to have both the best of the CMOS world for the control electronics and the best of the quantum technology, and the idea is to leverage all the 3D technologies that have been developed for the microelectronic industry. So as a conclusion, we have demonstrated silicon spin qubits in CMOS geometry, in standard CMOS geometry. What we are looking at now is how to design the 2D array. We have been able to demonstrate long-distance spin entanglement in 3.5 that we're going to transfer to silicon in order to have a backup option when we are limited in terms of size. And all this allows us to have the plans for large-scale architecture. So thanks a lot, and thanks a lot to the whole team who was heavily involved.
Thank you very much. And questions?
Enrique Solano. When you compare this to trapped ions or superconducting circuits, and you speak about thousands and millions of qubits, how can you cope with the crosstalk, fidelity of each gate, connectivity, one-to-one or only nearest neighbor, and so on? So what is, and the 3D, so what are your parameters or figures of merit for the scalability in that sense?
Thank you very much. So the question is, how do we deal with crosstalks in this silicon spin qubit? The point is that we don't know. The correct answer is nobody has demonstrated yet, so this is just plans. And the plans are, so we have some piece of evidence on how we can move away the electrons from one another and switch down the interactions between neighboring quantum dots. That's on one side for the quantum dots and as a consequence the qubits. There are also some questions on the crosstalks in the control lines because they are going to be capacitively coupled. So what we are currently dimensioning is the low-K materials that are going to be needed and the size of the lines, so that the capacitive coupling between these lines is not much than what is required in the time frame when we send the signal. So basically we are performing the whole RF modelization of the environment, playing on the material properties that all the database that we have to actually design those systems in order to decrease the crosstalks. And not suppress, but just do what is needed.
I have a question regarding your table with the implementations. I think at the photons one, you put operating temperature as 4 Kelvin. And now it's
that's for the photodetector. That's
all right, because usually you operate the photons at room temperature. You don't go.
That's because of the photon detector.
Depends on which photodetectors, because you can have also at nitrogen liquid or close to 0 degrees. So
yeah, agree with you. I would say that above. Okay, yeah, agree with you. That can be modulated.
Okay.
On the first table as well. So I see the point that we have a lot of experience how to work with CMOS and semiconductor industry and everything, but isn't it, this comes from a theorist, okay, from the outside. So when you see the lower line, then you know, some technologies also had problems scaling up from 2 to 3 to 4 and 5. Mm. What keeps us kind of, how to say, optimistic that if we haven't done 3 yet, I think there was only 2 entangled qubits demonstrated. How can we talk about hundreds of thousands? Is there something there that gives us hope, and what is it?
What gives us hope is the numbers. The reason, because we know the reason why we are stuck at 2 first, because we understand the reason why we are stuck at 2 is because we were dealing with with academic environment where the dimensions of the quantum dots are not determined by the lithographic dimension but by the material disorder, any remaining charge in the oxide, any interface state somewhere. And so far, we understand when comparing our systems with respect to the ones that were made in the labs. So that's one point, but that's a mature one. And the reason why we haven't designed yet more than 2 qubit gates, we also understand, is because so far what we have done, it costs a lot. So the only, do I have my boss in the room? No. The sample that we have used so far were designed for the CMOS industry. They were not designed for qubits. So we got started, and we got started with the CMOS transistors, and it had to be pretty much aligned with what was requested by the CMOS industry. So to provide you with examples, it means that at the beginning we were using high K dielectrics with density of states which are 100 times more than a silicon oxide interface. We were not having detectors close by the qubits because it does not comply with the design rules of the transistors. So this is what makes us optimistic, because we know why we are just at 2 qubits now.
So thank you very much. We have to go on. So let's thank Maud for the talk. And next speaker. So next speaker is Markus Greiner. Markus Greiner is professor of physics at Harvard University, and his research is focused on experiment with ultra-cold atoms in a regime where strongly correlated many-body quantum states can be experimentally realized in a well-controlled way. So he has contributed to several milestone experiments in the field of quantum simulation. In particular, let me mention, by loading the ultra-cold atoms in an optical lattice potential, Markus Greiner and his colleagues in Munich, they have observed a quantum phase transition from a superfluid to a Mott insulator. They have also created highly entangled states of light, and they have produced molecules via photoassociation. And then in another sequence of experiments with his colleagues in Colorado, they have demonstrated the first condensate of generalized Cooper pairs and accessed to the so-called BCS-BC crossover. And finally, with his team in Harvard, he has designed and developed a new type of quantum gas microscope allowing to study these systems with an unprecedented control. So thank you very much, Markus, for being here. And please.
Yeah, thank you very much for the invitation. Is microphone work? Now it is. It is a great pleasure to be here. It's exciting to see all the recent developments. I would like to tell you a bit about recent developments, recent breakthroughs, in a platform that many of you may not be particularly familiar with. So this is ultra-cold atoms. And let me show you a bit what we can do with that. Because what is nice is that ultra-cold atoms really give us a possibility to have a very large, very well-isolated quantum many-body system, strongly correlated quantum many-body system. So where we really have where we really get at a point now where we get a quantum advantage for studying very relevant questions, relevant problems, for example, relevant to material science, but also other fields in physics and beyond. And so I would like to tell you a bit of at first I will focus on fermions and optical lattices, and then give you a brief overview of some other recent developments. So when we work with ultra-cold atoms, we ultra cold means we cool them to extremely cold temperatures. We are as cold as the LHC is hot. We are 13 orders of magnitude colder than room temperature in our atoms, right? And that sounds hard, but at the end of the day, it's not that difficult to achieve. Use laser cooling and other techniques to get a gas of atoms to those temperatures in a vacuum chamber. The atoms are quantum mechanically delocalized then. So it's really the wave function that describes the position, but also the spin of the atoms, which is kind of our playground. And for example, we can load these atoms into an optical lattice. What is that? So we get a periodic potential landscape that is formed by light, right? And so the atoms move in there just like electrons move in an actual crystal. But they also interact with each other and so on. And so you will see that leads to really interesting physics. What is nice is that we can regard this as a model system for actual materials. And today I will tell you about how this can even be a model system for something like high-temperature superconductors, which are not really well understood. There are many open questions, and so we can now start to use these quantum simulation to really address these questions. We developed quantum gas microscopy. In the first 10 years of ultra-cold atom research, everything was just like a cloud of 1 million atoms, and you would take one shadow image in the end. We then developed techniques that we can really image all the individual particles. So here you see a Bose-Einstein condensate where before the picture is taken, every of these atoms that you see here is everywhere at the same time. Every one of these atoms is delocalized over the complete cloud. Only once we take a snapshot, we find them at particular positions, the wave function collapses. And if you look closely, you can actually see, in this case, they're an optical lattice, so they appear on a square grid here. Okay? But we can take a complete quantum snapshot in this quantum gas microscope. So it's a two-dimensional quantum gas in the focus of a very high-resolution optics. So we interrogate our atoms with light. And that is very nice because we can, that's very scalable. We can talk to many of them without disturbing others. So that makes it very scalable. We can take a perfect snapshot here with 99.9% fidelity or so has been demonstrated, even higher. But we can also turn the microscope around. We can use it to create arbitrary potential landscapes, arbitrary light pattern for manipulating the atoms or for programming a Hamiltonian. So this becomes very programmable. I can really set the potential landscapes, tunnel coupling, spin, manipulate the spin completely locally without disturbing other atoms. And so this makes it a very rich, very scalable platform where we can program a wide range of Hamiltonians. Okay. Let me show you, how do these atoms move in the lattice? Well, they don't move certainly like a classical particle. They move fully quantum mechanical. So if here I prepared initially an atom on each of these lattice sides in the vertical row, and what do you expect if you now let the atoms tunnel? The atom is described by a wave packet which is initially localized, and then it delocalizes like this. But what this means is that the atom is really completely coherently delocalized left and right in a superposition. And if you take a snapshot, each picture in the movie is a new sample that we prepare and get a new snapshot, then we find the atom sometimes left or right. But before we take the picture, it's left and right. It's coherently delocalized. How coherent? Extremely coherent, which you can see because we tilted this lattice, so you get a Bloch oscillation. And what that means in real space is that the wave functions rephase again, and the atom ends up exactly on the original lattice side. The only way it can do that is by delocalizing coherently, and there's no dephasing or so it comes back perfectly to the same side. So this shows you the degree of coherence we have in the system. This goes on over many, many oscillations like that. Well, this you could also do with photons, but what is great with atoms is that they can strongly interact with one another. And they can do so without hurting each other, without introducing loss or so. Okay? And so this gives rise to, if you now have many of these atoms and they interact, for example, a quantum phase transition from a superfluid where each atom is delocalized coherently to a mod insulator where you have exactly one atom per side. But the important thing is this is really a strongly correlated quantum state, and we can cross back and forth. What I would like to tell you about today is not this bosonic atoms that behave like photons would do, except they have a very strong single particle nonlinearity, like interaction. Instead, let's talk about fermionic atoms. It's actually great to do quantum simulation with fermionic atoms. You all know, in principle, you could study, first of all, there are many interesting fermionic problems in chemistry, material science, right? In principle, you can compute them on a quantum computer, but there's a huge overhead if you do a Wigner transform and you kind of, a quantum computer is inherently bosonic. Fermions seem to be a different beast in many ways, so if you want to do that on a quantum computer, it becomes extremely non-local. With the fermionic quantum simulation, we have an inherent advantage of really having the fermionic degrees of freedom in the first place. So let's do that. Atoms hop on the lattice, so all they do is they tunnel between neighboring lattice sites, and they, if there are two on the same, so the two different colors denote two different spin states, two on the same side, that raises the energy by an on-site interaction U, and they can tunnel. So that they repel on the same side, they tunnel. Really simple, right? It's really deceivingly simple Hamiltonian. This is called the Fermi Hubbard Hamiltonian. It's the simplest non-trivial fermionic Hamiltonian. It turns out this Hamiltonian is not really understood well. And it is extremely hard to compute it. Okay? For example, it is believed that the phase diagram looks pretty much like the phase diagram of cuprates, of high-temperature superconductors, which in itself isn't really, there's no unified picture of these phases, which you can tell by looking at the name, like a pseudo-gap or a strange metal. The point is that there are many open questions. There's no unified understanding. What is really the microscopic physics that gives rise? For example, is the superconducting state competing with the antiferromagnet, or does it emerge from the antiferromagnet? And if so, how? These are all questions that are not understood. Right? So the amazing thing is the simple Hubbard Hamiltonian that we have a perfect realization of in the lab can already address these kind of questions. And if you understand that, of course, that may really help ultimately also to understand other actual materials better. There has been a lot of progress, but having these quantum gas microscopes really gave it a boost recently. And so let me show you what we did recently. The Hubbard model at high temperatures, it's a metal. If you cool it down, you get a mod insulator. But at really cold temperatures that we were recently able to achieve, then the atoms start interacting magnetically via superexchange. Essentially, two atoms in two different spin states can virtually explore the neighboring lattice sites if they're in the opposite spin state. But if they're in the same spin state, then Pauli exclusion forbids you to even virtually explore the neighboring sites. So at the end of the day, at half filling, where you have a mod insulator, you expect, you essentially get a Heisenberg antiferromagnet. Can we see that? So recently we have been able to see that. Here we image only one spin state, so a dark spot is a spin down, and a blue spot is a spin up, and so we see a very nice checkerboard. So yes, we have been able to get into this antiferromagnetic state, you can see as we lower our temperature, the correlation length really gets very large and gets ultimately larger than the size of our sample. One important point to point out, this is not a simple checkerboard. It's kind of like a Heisenberg magnet. There's a lot of quantum correction. It's much more quantum than just a simple up-down checkerboard. But for the rest of the talk, I kind of approximate it as more or less a checkerboard, but keep that in mind. So that was exciting to reach this kind of state, but honestly, without doping, you can calculate it. It's Heisenberg. It's pretty much Heisenberg. In any case, you can solve the Fermi Hubbard at unity filling with one particle per side. You can solve it. It's not computationally hard. There is no sign problem. Quantum Monte Carlo does the trick. But what happens if you now dope, if you put in additional charge carriers, holes or doublons? It turns out that then immediately a very a severe sign problem emerges for quantum Monte Carlo, and it is extremely hard to do any computations in these regimes here. You can maybe try to calculate the absolute ground state, but or you can come from top to roughly the temperature, like roughly where we are. That's kind of the limit of what can I mean, it's a moving target, but this is kind of, we are exactly at the point now where it gets incredibly hard or impossible to compute. Now, why is that? What makes it so different if you now have doping, if you now have additional charge carriers? Let's first talk about one-dimensional systems. In 1D, so here we have prepared a chain of atoms, just like what I showed you earlier with the single atoms tunneling. Let's prepare an array of 1D magnets here, and then I put a hole in by hand, because as I told you, we can program potential landscapes, so let's keep one row empty. Here's holes. How would these holes move? Let's do the same experiment we did with a single atom, and let's move this hole in this antiferromagnet. And we let the time evolve, take a snapshot, and we find, if we plot that, we get a perfect quantum walk of the hole, just like what you would expect for a free particle, right? Well, that doesn't sound complicated. Yes, in fact, in 1D, you have perfect spin-charge separation. Essentially, if you look here, a hole can freely move in the magnet without disturbing the magnetic order. It's completely decoupled. Very simple. The funny thing is, in condensed matter physics, it's actually hard to detect that, because you think that if you dope, your order has disappeared because there's always an offset here in the magnet. But if you go to squeeze space, where you just take out all the holes and shove it together, you have a perfect magnet again. With the single-side imaging, we can detect that directly in conventional ways. To measure this in a material, you would think the magnet has disappeared, but it hasn't. It's really spin-charge separation, and this hidden order here prevails, and it's simple spin-charge separation. Okay, nice. The good thing is that the interesting thing is in 2D, the story completely changes. And that's where you can see where this richness appears. Look, imagine for simplicity a classical magnet here. So keep in mind we have a bit more quantumness. Imagine there's one hole here. If this hole moves now, look, there's a row of atoms that are, or of spins that are in the wrong spin state, right? And let's call this a string here, right? So this is a row of atoms. You can, by looking at the spin, you can tell which path the hole went. There's entanglement between the spin and the hole degrees of freedom. And there are some recent ideas that maybe this actually makes up a good microscopic model for what happens, for example, in cuprates. You could say that the end here, there's an extra spin, so this is a spinon, and maybe this is actually a stable object. Maybe this is connected via a string. The hole is connected via a string to the spinon. And then you have a gas of mesons, so the string could break, then you have holon, string, holon, that's a magnon, and a new spinon, string, holon. So maybe you can think of it as gas of these particles, right? And maybe you can even understand why Cooper pairs form. The point is, nobody can currently answer these questions computationally, okay? So let's have a look. Do we find any evidence in our experiment, in our quantum simulation, of these kind of strings. So we take large number of snapshots here, and then we can analyze the snapshots. I don't go through details now, but we can essentially look for these stringy objects, okay? We can count, we can take histograms of how many strings of what length do we find, and compare that to some simple naive theories, for example, right? Or, right, and then we can see, is this compatible to what you would expect if you just have a magnet and sprinkle in holes? Or maybe it's compatible to actually having a magnet and applying these strings corresponding to some recipe from some effective theory. Or you can also compare it to completely different theories. For example, a spin-liquid theory with rotating valence bond states. So here's a plot of the string length distribution. So this is the length of the string versus how often we find it for the undoped magnet. Well, the point is, even in the undoped magnet, we have a, so as I said, it's a quantum magnet. So there are already coherent excitations in there, like local singlets, and that gives rise to this background of strings. But if you dope it, we find indeed roughly half an order of magnitude, up to 1 order of magnitude more strings. We find many more strings here. And this is the string length distribution. And we can now compare to different theory. And surprisingly, this kind of effective theory where we assume that these strings form from the holes moving, this gives a very nice agreement. So we were very excited to see that. And if you go to higher temperatures, then all of this seems to disappear. So this is really like getting into this pseudo gap, or so we have some first evidence that maybe a picture like these strings may actually be a valuable picture. So we can really start to address these questions now and can test different theories. Here again, versus doping, how many strings do we find? This is what we find. This is the corresponding theory. It's not a full theory. It's a kind of we kind of have some simplified theory that gives us a string length histogram without any free parameters, and then we apply it to undoped samples and compare that. But we can also compare it to the spin liquid states, and actually that also didn't do too bad here. It doesn't agree as well, but I would not say that we have ruled out or strictly confirmed something. But you can see how we can now really start to address these very, very hard questions that can not currently be computed, right? So maybe it's true. If we find that there are these strings and they are fairly stable objects, well, we can do the next step now. Like in 2D, we could also inject holes and see, do they form these strings, or we inject 2 holes, right? And then we could see 2 holes, do they move independently, or do they move in a correlated fashion? If 2 holes would move in a correlated fashion, maybe that's a Cooper pair, right? And we can look at the magnetic environment and see, okay, why do they form Cooper pairs? So these are the kind of things we currently work on. So it's a completely new paradigm, because you imagine if it's hard to calculate equilibrium of the Hubbard model, non-equilibrium is much harder. Essentially, all you can do is exact diagonalization, which means on your laptop you can do a 4x4, and on a supercomputer you can do 4x5 lattice sites, essentially. But here we can really study this dynamics very nicely. And then once we see what actually happens microscopically, of course, we can also look what are the quantum phases it gives rise to, what quantum phases emerge from that. We want to get colder. Recently, we were able to make a band insulator that is actually that is much colder than what we currently have in the magnetic, in the antiferromagnet. So we have extremely low entropy per particle. And so now we develop schemes. How can we, like initialize our quantum simulator with this extremely cold, like we really only have 1 excitation in a few hundred of these fermions. 1 excitation per few hundred fermions, and we can time evolve it over hundreds or thousands of tunneling times without creating additional excitations, right? I mean, that's how we got this state in the first place, right? So it's really an amazing quantum volume we have here. And you have fermions where we have this intrinsic advantage if you want to understand fermionic problems. Okay. There's a lot of related work going on in Munich in particular. In Princeton, my former student, Wasim Becker, who recently studied the bad metal, the strange metal phase. And in fact, he found linear T-dependence of resistance, which is kind of the hallmark of this strange metal, or you can look at spin transport. There's a lot going on. In the last few minutes, let me just flash a few other things that we're currently working on in quantum simulation. So Fermi Hubbard is one really exciting thing where we can have a quantum advantage, but also with bosons, it becomes extremely hard to track computationally once we go to a non-equilibrium situation. Right? And so here we did an experiment where we study quantum thermalization. That's actually, it's kind of funny. Let me just give you a very brief version of the story. If I have a closed many-body system here, initialized in some eigenstate, like a mod insulator here. If I then hit it with a hammer, if I quench it, okay, I create a non-equilibrium state. But importantly, it's still a closed quantum system, so this evolves under completely unitary dynamics. So this always, if this was a pure state, it remains a pure state. We can measure that directly. We can measure if we have a pure many-body quantum state in a 20,000 dimensional Hilbert space. How do we do that? We can create two identical copies, and then we interfere them. But it's not interfering light or Bose-Einstein condensates. It's like Hongu-Mandel interference. It's really a many-body interference, and the parity signal tells us the quantum state overlap between the two. And we see that we have nearly perfect quantum state overlap, even for fairly large systems, very long coherent evolution, and we can measure it directly. Okay, but this means the state remains pure, no entropy. At the same time, any local measurement after the quench would tell you this looks thermal. Right? Any local observable is indistinguishable from thermal. Okay, and how can that be? I mean, this is maximized entropy. This is no entropy. We just show there is no entropy, but here it looks thermal. It's quantum thermalization. It's the entanglement in the system that builds up. That if you only look at part of the system and you trace over the rest, that entanglement entropy becomes the thermodynamic entropy. It's kind of like you can view this as a mini model of the universe, even if the universe was in a pure quantum state. I'm not saying it is. If it was in a pure quantum state, any measurement on less than half of the degrees of freedom would actually tell you that it's just a classical thermal result. So this is interesting. You can see how statistical mechanics emerges naturally from coherent Schrödinger dynamics. Have a look at the paper if you are interested in that. We studied recently many-body localization. That's a breakdown of this thermalization. Importantly, we were able to look at this kind of hallmark signature that we see the logarithmic entanglement growth in MBL, which was elusive to see so far. Then we can also study, the quantum critical regime. Like, this is a really interesting phase transition. It's not, there's no simple order parameter. It's from thermalizing to not thermalizing. And we found that in the quantum critical regime, that's where it's really quantum, because we found that you need very high order, you still find non-vanishing high order correlation functions only in this regime. Currently, we did these experiments at a system size where you can just exactly calculate it still, just at the edge, kind of what you can still calculate, because that way we can make sure what we see makes sense. But if you just make the system 2 or 3 times larger, we're solidly in a regime where you cannot compute things anymore. Last but not least, so here I was talking about physics problems. Recently, we started a collaboration. It's led by the group of Misha Lukin, together with my group and Vladan Vuletic's group. And this is building on ideas from Paris, from Antoine Beauvais and Philippe Lagrangier. The idea is that you trap in a tweezer array atoms, and so you can create an array of atoms. They're not vibrationally at the ground state, but they don't need to be, and we can just sort them kind of to make a perfectly filled array of atoms. And these are very nice qubits now, and we can use Rydberg states to couple between these qubits. And I don't have time to talk in detail, but essentially you can program very interesting Hamiltonian with that. You can create entanglement. We just created a GHZ state of about 16 of these, up to 20. And you can study non-equilibrium physics in regimes where it's extremely hard to calculate. But there are ideas out there how you can even use them to help with problems not from within physics, namely optimization problem, general optimization problem. There are interesting proposals how one should be able to use such a system to realize a quantum approximate optimization algorithm. This is like a problem of a maximum independent set, kind of, and for that you would just have to arrange the atoms in a graph essentially, and then with a Rydberg, it turns out with Rydberg interaction you can kind of map this, and so this is a fantastic playground to look, can we also do optimization problems with these kind of systems. So these are only light patterns, not atoms yet, but we are about to load atoms into that with the same techniques. You see it's certainly very scalable, and then if you can program kind of arbitrary positions, we may be able to, so I'm really looking forward to look into that. Okay, I think it's a really exciting time. With a cold atom, it's really amazing how much many-body coherence is available now to do a very wide range of experiments. And so with that, I would like to thank my group. The main topic I talked about was done by these students and postdocs, and I would like to thank you very much for your attention.
Thank you, Markus. So, questions?
Yeah, Markus, in these trajectories left behind by the moving hole, I wondered. I mean, I think it becomes non-unique as soon as you have more than one hole, right? So I wonder how you cope with that.
So first of all, it's all quantum, right? So meaning that the hole delocalizes around the spinon, but it does so in this interesting way of simultaneously taking all these different possible paths, ways, right? And nobody knows what would happen if you now have two of them, how they would interact, right? You could so we want to study now how two of them would actually interact and maybe lead to, attraction, maybe lead to forming Cooper pairs or preformed pairs for now in the pseudo gap regime or not, right? If you go back a step, you can actually say, so one of the big open questions is, does superconductivity in high TC emerge from the antiferromagnet or compete with it? Well, maybe it really emerges from the magnet. If the string picture was true and the Cooper pairs come this way, then even this phase diagram of the antiferromagnet is misleading. If you go beyond, you still have an antiferromagnet, but there is a spaghetti of these strings. And they hide the magnet from detection methods that are available in condensed matter physics, because they only look for long-range order, okay? And so maybe it is that there's the soup of spaghetti, there's still a magnet, but you don't see it, it's in some complicated hidden space.
Ramen, rather.
And that may what actually gives rise to the pairing. Or not, right? I don't know, but these are the kind of questions we can now try and study experimentally.
Hi, I'm Dimitris Angelakis. On the thermalization, many-body localization experiment, so you measure global properties, I guess. There's a very large system, and you can see because you don't have local control. So there is the complementary approach.
We do have local control,
but not correlation functions on log like XX and YY. So what we've seen in the superconducting experiment with John Martinez, we had a very recent work on that last year, is you can get the mobility edge as well on top. How every state, you can actually unravel every eigenstate and see how they change from localized to extended. Of course, it's a small system. It's only like 9 or 10 qubits at that size, 10 sites. So what I'm wondering is whether there is an intermediate regime. So this is a bottom-up approach when you have, ions or superconducting systems that you can probe signatures of this phenomena. And then there's the top-down where you have many real, a lot of thousands of atoms, but you're lacking the full control that the other systems can give you. What is this kind of intermediate regime, whether there's a phenomena or interesting phases that one could
right. I mean, what is nice with the atoms is, so currently we did experiments building it up, 6, 8, 12, soon we'll do 24, 36. So you can kind of build it up, and in that regime, we can actually make sure it remains a pure many-body quantum state, kind of. So we can even post-select or not having lost any atom or things like that. If you go to larger and larger systems, at some point you don't have that anymore. So first of all, the bottom up, you can actually push up pretty far. And it then depends on the kind of observables you look at. Some observables really require this kind of finite size of the system, but other observables like high order correlation functions, you can also apply for bigger systems, right? And so just like the very first picture I showed you, we could apply those high order correlation functions to a shot of 10,000 particles or so. That shouldn't be a problem. So, but oftentimes we may face the same problems like in numerics, right? In numerics, if you want to see like where the diffusion becomes anomalous in MBL, well, you need a large system to do that. So in numerics, you study it for 6, 10, 12, and 14 sites, right? And then you extrapolate that, right? Of course, we can do the same. In fact, in our last paper, we do something similar where we see the finite size scaling. Also keep in mind, this is Bose-Hubbard. So if we have an 8-site system, that's the same Hilbert space as about 16 spins.
So, yeah, maybe we should stop here, and let's thank Markus again. And,
you want this microphone? Yes. Yes, please.
So the next speaker is Hugo Zbinden. He's professor at the University of Geneva in the Quantum Technologies Group, and he's also one of the founders of Idée Quantique. He works on experimental quantum information and communication, single photon detection, and optical sensor. He has performed a seminal experimental demonstration of both quantum cryptography and teleportation, and he has demonstrated the record-breaking distances for QKD. And also, he has demonstrated the first quantum random number generator, and his results have significantly contributed to the development of practically secure and large quantum scale cryptography networks. So thank you very much.
Thank you. Can you hear me? Yeah? Okay. Well, thank you very much for invitation. And indeed, this afternoon I will talk to you about long-distance QKD. And essentially, I will present you this paper. And this allows me also to introduce a bit my team. So you see here Alberto Buaron is a PhD student who made most of the work. Then I have a few people, like Davide, for instance, is also here, who works on the theory. And then there are a few people working on the superconducting detectors, and actually also a few people from Corning, which supply the fiber. So, well, this distance, 421 kilometers, is up to now the longest published distance for a QKD. Well, it's actually not the result of a single breakthrough or a single effort. It's actually a result of improvement on many, many different scales. And this gives me also a bit kind of outline of my talk. So first I will talk about the QKD protocol we implement. Then a little bit more about the technical thing, how to realize a fast system. Then of course you need very good fibers and flow loss, and also low loss and efficient detectors. Okay, so I don't know if you are all familiar with QKD, but probably you heard about this famous protocol, this BB84 protocol, where Alice sends randomly one out of four different states to Bob, and Bob measures in two non-orthogonal bases. One way to realize this is using this kind of phase encoding. So actually, you send a laser pulse through an interferometer. So now you generate two pulses, and you have a different phase between these two pulses, no? And you can vary this phase. We have different values for this phase. And now Bob, he said now these two pulses in interferometer, so in a way that the first pulse will take this long arm, and the second pulse will interfere now with this first pulse. And depending on the phase he chooses here, he can measure in one or the other basis. So now, in the normal BB84 protocol, you randomly choose these four states with an equal probability. And the same for this basis with a probability 1/2. Now, one way to improve that or simplify that is, first of all, you can say, okay, instead of using these four states, which are here on this qubit sphere here on this equator, I could also choose actually two states which are just on the poles, so this in a computational basis, and only two states out of this equator. That's the one thing I could try to simplify. And then, in order to improve the efficiency of a protocol, I can say, okay, I send most of the time in the same basis, and Bob will also most of the time measure in the same basis in order to improve as much as I can the useful bits. And then from time to time, I just measure in the other basis to check for the security, to see if an eavesdropper is around. No? That's the idea. So if I combine these two ideas, I come up with a protocol like this. Now I have a C basis is my databases, so I have now a 0, which will be a pulse in an early time bin, and a 1 a pulse in a late time bin. And then I have the X basis, where I can send two pulses in a superposition between early and late with different phase. So this is the standard way to do in this kind of basis, no? And on Bob's side now, what I can do, I send the light pulses either directly to this detector, which just detects the arrival time of a photon, which is a very simple measurement, which does not introduce a lot of errors. And then part of these pulses will go, this is a passive coupler here, part of these pulses will go to this detector here, to this interferometer here, where I can check if this phase relationship is still the same. And the idea is that when an eavesdropper tries to measure when pulses arrive, she will destroy this phase relation between pulses, and we will detect that in the X basis. Okay, now let's complicate the things a little bit. This, what I told you, was fine with I used single photons. But now we would like to use weak laser pulses. And if we use weak laser pulses, of course, it happens from time to time. We have more than one pulses, and there is a attack, which I will explain a little bit on the next slide. And for this reason, what people normally do, they use this so-called decoy step method. This means that I don't only send these pulses as I explained before, but also with different intensities. So normally people use 3 different intensities: the signal intensity, a first decoy intensity, and the third decoy intensity is just the vacuum. So why do we do this? So you know, if you have a weak coherent pulse, then I have a photon number in this pulse is a Bostonian distribution, no? And even if I choose weak pulses where with average photon number of 10% or something like this, 0.1, I will always have a certain probability to get 2 or more photons in this pulse. So now if the loss between a link of Alice between Alice and Bob is quite high, the eavesdropper can actually concentrate on the pulses where there is more than 1 photon, take 1 photon and send the other photon to Bob on his own fiber, which has less loss, in a way that Bob still gets exactly the same amount of detections like he expects, but now Eve can actually have almost all information because she keeps 1 photon of all out these pulses. Now, this decoy state method tries to fight against this, no? And the idea is, I will not go too much in details, mathematical details, but the idea is actually quite simple. You vary the intensities of the pulses, and then, of course, you would also expect at the end a probability of detection which should be proportional to the intensity of these pulses. Now, if Eve makes this photon number splitting attack, she will actually concentrate more on the pulses with 2 or more photons. So she will let pass more the stronger pulses than the weak pulses. Yeah? So this is the probability distribution what you'd expect. But if Eve makes this attack, actually what will happen, it's a bit exaggerated here, but the probability to detect the stronger pulses will be higher than what you would expect. So what you have to do, you have to estimate now a contribution of all these pulses which come to Bob, where originally you had 0, 1 or more, or 2 or photons or more. Okay. Now, it turns out, so you see that you have different intensities, you have all these statistics, and you try to look if the statistics fits to your expectation. And now, in our security proofs, we have to do what we call a finite key analysis. So we have to take into account all the statistical fluctuations we may have in these distributions. And if the sample size is actually quite small, these fluctuations can be very big. And still, we always have to assume that the eavesdropper is lucky, and we have always to calculate with the worst case. It means that actually we can extract only very few secret bits. So this means that actually, if I come back to, this means that these pulses here are, in principle, in theory, very useful in order to determine this fraction of 0 photon events. But in practice, in this finite key scenario, actually, the penalty is too big. I have to send a lot of these pulses which don't contribute to my bit rate at the end, and at the end, it's actually not so efficient. So if you analyze that, you find out that it's much better to use just 1 decoy state. And that's what this is a graph from this study of in this paper here. It shows you that actually by using only 1 decoy state instead of 2, you actually can improve the secret key rate for most cases. No, you see here the range of attenuation in my link, and you see that between 20 dB and 60 dB, actually the one decoy state is actually always better. In the case where you have a finite key scenario. Of course, if I have an infinite key length, then our two-K state protocol is more efficient. Okay, so this means that actually we can simplify our protocol a bit further, no? We remove this part here. Okay. Now, actually it turns out if I test the security of our system in this X spaces, I don't really need to send both states. I actually can send one of those. So I can simplify it again. No? So now I remove this state here. So instead of having 4 states with 4 different outcomes, actually now we work with 3 states and just 3 outcomes. And we managed to show this security of this protocol. Well, you might think that it's not so important. I simplified a bit, but actually in practice it's very helpful, no? Since I don't have to change the phase between these 2 pulses. Now, if I would like to send the plus state and the minus state, there is a different phase. Now I don't have to change the phase. I just have to change the intensities of these pulses. So it means that I can have a setup now with just a single intensity modulator. Okay, that's an advantage, no? So let me explain a bit now how we realize this, no? And well, here you see, I start with a pulsed laser, and which is clocked at 2.5 gigahertz. So we have 400 picoseconds between 2 pulses, and it's very important that the phase between these 2 pulses is random. So we have to verify that even if at these high rates, we have that these 2 pulses have a random phase. If this is not the case, Eve can make some what's called coherent attacks, and she can get more information. So if we want to prevent that, we must be sure that these phases are random. Okay? Then, well, actually, that's a kind of a technical detail. We put a spectral filter. And actually, this spectral filter helps us to shorten our pulse. Because our pulses are not Fourier limited. We have a chirp, no, in our laser pulses, in this gain switch phase. So by putting a relatively narrow filter, we can shorten the pulses a bit. So we are fully limited here now after that, no? And we get pulses of roughly 30 picoseconds. Then we send them in this interferometer, and now we have 2 pulses, no? And here we don't change a phase, no? It's a given phase relationship now between these 2 pulses. And now, these pulses come on this intensity modulator where I modulate the intensities in a way to get this pattern, no? So if I want to send a 0, I block the first one, I let pass the second one, and so on. And then for the decoy states, I just reduce the intensity bit. No? Okay? Well, then it turns out that if we go to very long distance, this chromatic dispersion becomes a problem. So I have to compensate the dispersion, what I do with this dispersion compensating fiber. And then at the end, I add an attenuator where I can adjust the average value of intensity to correspond to what I want, which is normally, in our case, roughly 0.5 photons per pulse for the data pulses, no? For these ones, no? And this is half of it, no? Okay? Well, now, that's just my protocol. Well, now on Bob's side, I have, as I have seen before, now I have a beam splitter. When measuring the databases, I measure this arrival time of pulses with a superconducting detector. And then I have this interferometer which checks for the coherence, and I have a signal detector here. Okay? Well, now I can have a all-fiber high repetition rate source. So if now we look at this picture of our source, you hardly see fibers, no? There are a few here. And actually, most of the source or the challenge is actually a technical challenge to make these high rates and to control the whole system. No? So in Alice and Bob, we have FPGAs, which we use to synchronize the two systems. We have to synchronize it to below 100 picosecond, no? And then we have to use a feedback mechanism to control its timing, to control the phase of interferometers. We have to generate random numbers. We have to then to apply this pattern to the integrated modulator. And then at the end, we make the sifting, or error correction, privacy inflation. All this protocol can be done in this FPGA. If we are in a case where we have low rates, we can also use just a computer to make error correction and so on. But if you go to a fast version, you better do that in FPGA. Okay, so that's about the hardware. About the fiber, there's not a lot to say. We just choose the best fibers you can get, no? And you see this is 400 kilometers of fiber in these boxes. And normally, in average, these fibers have kind of 0.16 dB per kilometer loss. And now, of course, you have to connect them and so on. So at the end, you end up with something like 0.70 dB per kilometer. A bit more interesting are the detectors. So we fabricate ourselves our detectors. And these are superconducting nanowire detectors. And our material is molybdenum silicide. And we work at a temperature of 0.8 Kelvin. You see a little bit how this works very briefly. No? You have this nanowire, this is a very thin wire. And you see here a zoom of this wire, and whenever a photon hits somewhere, is absorbed in this wire, actually what happens, it creates a hot spot. So what we do, we send a current through this wire, which is below the critical current of the superconductor. And whenever now we heat it up, there's a mechanism which is actually not so clearly understood. But at the end, we come up with a zone where the superconductivity is broken. And so this is a resistive zone. And now we can detect a voltage pulse out of after that, not because we have a current, all of a sudden have a resistor, and I can detect that. So the performance of these detectors is very good, no? So we can achieve 85% of quantum efficiency. Now, in our case, if you want to go to very high distance, what is really important is actually the noise. And now, it turns out that the inherent noise of these detectors is actually close to 0. So the noise comes actually from a black body radiation, which comes in through the fiber to the detector. So we can remove part of that by using, or most of it, by adding a filter, no? A spectral filter. Unfortunately, this spectral filter at this cold temperature introduced some loss. That's why at the end, our efficiency is only 50% and not the 85% what you could expect. But then with this, we can reach rates, almost arbitrarily small rates. We normally work with something like 0.3 counts per second. Okay. Now, well, if we put that all together, we can run our system. And here you see a kind of a run over many hours where we test the stability of our system. No? So what do we see here? These red circles, no, sorry, this start here. The black points here is our raw key rate. So that's the rate with which we detect our photons. And now, down here, you see the quantum bit error rate we have in the C basis. And these blue dots are the phase error rate, which we estimate from a visibility we get in our interferometer, no? And these together gives us the information of the activity of the eavesdropper, and then we apply this process, which is called privacy amplification, to generate a secret key. And you see what we do here, of course, we have to reduce the rate a bit, no? That's the price to pay now. So we start from this raw key rate, which is not secure. Now here, Eve might know some bits to a secret key rate, where now we can define a security parameter, which in our case is 10 to minus 9. So we can say that only if a chance of 10 to minus 9, Eve might have information about the key. That does not mean she knows all the key, but she may have a little bit information. So this is at the distance of 300 kilometers. So everything is running automatically over many hours, no? Well, now let's have a look how this evolves as a function of distance. So we see, well, of course, here is the distance, no? And then we have our loss, and we have this logarithmic scale here, and our rate goes down exponentially, no? So we start at something, so around 300 kilometers, we have 1,000 kilobit, 1 kilobit per second, and at 400 kilometers, we have just approximately 10 bits per second. And then at the very end, we kind of add an additional point where now the statistics becomes very bad, and our algorithm to make all the adjustments is no longer so good. So we have to kind of manually readjust from time to time. So that's why the rate blocks really goes down here quite a lot. So that is the maximum. Okay, so that we are quite happy. We go to 400 kilometers, and you see here a comparison with former experiments. So we are pretty much faster, like 2 orders of magnitude with respect to these experiments here. And here the difference even bigger, but to be fair, we must say this is an experiment where they use the measurement device independent scenario. Okay, now how far can we really go? And well, first we could say, let's compare our system with just a kind of an ideal system. No? If supposing that we don't have any technical limitations, but we keep the same repetition rate, but now we say, okay, we have no detector noise, we have 100% efficiency, and so on. And this gives us this green triangle. So we see we are reasonably close to the best what we can expect, which is, of course, somehow good news, because we say, oh, we're pretty good. We cannot. But on the other hand, it's also bad news, which it shows a bit the limits of QKD. No? So if you go a bit further, how far could we really go? You see here. So this is now even a bit more optimistic. We have now a bit of faster repetition rate, 40 gigahertz, but essentially also 0 dark counts and 100% addiction efficiency. And of course, if you have an infinite key length analysis, then it's just a straight line, and it goes down exponentially forever. No? But now, since in order to extract the key, you need certain statistics, then at some point you need to start to make your distillation, no? And now we fix ourselves a time. So the time is now fixed to 1 day. We say, okay, maximum after 1 day, I would like to start a key distillation. So if I apply this, and with this security parameter here, then at some point it breaks down, no? So you see, it's kind of 600 kilometers what you could achieve. So now, this is the case for this transmission, as I just said, no? Sending a photon from A to B. Now, maybe you have seen this week there were two papers coming out where people presented a realization of what is called twin field QKD. I will not explain you what this means, but essentially in this scheme you can kind of divide the distance by 2, or the other way around, rather. So you can double the distance. So now these experiments we have seen this week, they are, I don't know, one was over 300 kilometers with very low rates, no, there's something here. But the scaling is different, no? So if you have an experimental point here, we have this slope, but in this twin field thing, the slope will be half of it, so it will be like something like this. So eventually, one day, with this twin field technology, you might reach more than 600 kilometers. So, yeah, so I come to the end here. So, no, just before I stop, well, I was concentrating on long distances, no? Now I would like to see what happens if I go to shorter distances. And so you see here now a plot of our, that's what you have seen before, this is our experimental result. And actually, oh, that's really a bad quality anyway. And actually, we are now limited by the maximum detection rate of our detectors. So we put the emphasis of the detectors that we have low noise, but they are relatively slow. So now currently we are working on a new generation of detectors where we would like to have higher detection rate. And if I extrapolate now with the new detectors, we will move on this curve here. And eventually what we expect, hopefully soon, that we could generate 100 megabit per second at short distances. So here you see as a comparison, this is this result from Toshiba, roughly 10 megabit per second, which is the highest rate detected, realized up to now. And actually just to compare with the CVQKD, you see here the highest distance what was reached up to now with CVQKD. Okay, so I think I'm almost at the end. I come to my conclusion. So I have shown you that we can make QKD over 400 kilometers with these superconducting detectors. If we use indium gallium arsenide APDs, which are of course much more practical because we can cool them with a Peltier, the distance we achieve is around 300 kilometers. At short distances, rates of 10 megabit per second are achievable. Well, now, of course, in future, we would like to make it simpler, smaller, and cheaper, and whatever, and eventually come up with a commercial product like this. Thank you very much for your attention.
Thank you very much. Questions?
Very nice. Did you consider also the possibility of hacking? That is classic. For instance, if anybody can manipulate the entrance beam splitter at Bob's site, you are sort of dead. So you see some remote manipulation of this beam splitter would kill the protocol. I think so. So did you just look at that, you know, Makarov type attacks?
We, of course, in this case, we didn't really implement many countermeasures, but indeed we have to trust the beam splitter so that nobody from externally can try to influence that. I don't know how. But what actually in these hacking attacks happens, they attack the detectors. And now what we do, we currently developing detectors with many, many pixels. And this would be a good countermeasure against these blinding attacks, because then we can see if normally you would expect, and then one detector just one pixel clicks, and if eavesdropper tries to make these blinding attacks, then of course all pixels will click with a high probability. And this is one of different countermeasures you can think about. Yeah.
This specific protocol, which is sort of very sophisticated because you simplified it at the maximum, it doesn't make it more vulnerable to hacking attacks. I don't have any immediate ideas, but...
No, I don't think so. I think the kind of weak points are still the same. And the protocol, as it is, has the same kind of proof like the complete BB84 protocol. Yeah, of course, the hacking is, I mean, that's the thing. No, we have a model of our system, and according to this model, if we can prove that it's secure. Now, if the implementation has some defects, then of course we cannot prove it. No, but I think that's true for any cryptographic system. No.
Hi, Hugo. It's nice talk. And you mentioned the 50 kilometers, 10 megabits per second, the secure key rate. Is that the same paper you mentioned or a different paper?
Sorry, I think?
You mentioned the 50 kilometers, 10 megabits per second secure key rate in your last page.
Sorry, which one?
The conclusion. Yeah, here, back.
This paper here.
Next page. Sorry. Sorry.
Here.
The last second pages. Go forward. The last second pages before the acknowledgement.
Sorry.
Next one.
No,
Yes.
I don't have
Here you mentioned the 10 megabits per second.
Yeah. Sorry. Well, that's a bit kind of exploration of here. No, this 10 megabits per second was already achieved for Toshiba, but it was for very short distance. And we expect that with our system, we could have 10 megabits for at least for 50 kilometers.
With a high count rate detector,
Yeah,
you
yeah,
have,
yeah.
okay.
Hi, Hugo. I have a little bit of a more general question. So do you expect to solve the problems of the higher photon components by using photon number resolving detectors or single photon sources?
No. That's really this decoy state method which we count on. Yeah. And of course, single photon sources would be very nice, no? But the problem is, with this decoy state method, now we can work with 0.5 photons per pulse. So a perfect single photon source could help us to win a factor of 2 maximum, no? But now, unfortunately, if you look at the single photon sources, true single photon sources which exist today, most of the time you have a big problem of coupling the photons into a fiber. So actually, in fact, those sources are less bright than 0.5 per pulse. And then there are other problems with repetition rates are not the same and so on and so on. So for the time being, I think it's not really a solution we consider.
And for photon number resolving detectors to detect the higher
Yeah,
components,
I'm not sure
is
if
it
a photon
a
number
viable
resolving
solution?
detector could be a tool to fight against hacking, as I just mentioned. But it's not a solution to get rid of these 2 photon pulses, no? Because Eve will take the photon out before.
Anyways, right? They will take anyways. Yeah, true. Thanks.
This is not a well-formed question, but sometimes the security of a system is about knowing when the system isn't behaving as expected, which maybe someone's smarter than you and is hacking you, but you're not aware. One defense in classic networking is to reset boxes, to effectively reset them, and especially in crypto. In this concept, is there a session kind of concept? Let's say you're transmitting very, very long keys. Would there be any indicators you could use that you say, I need to reset this, or is it simply that every transaction is discrete and you trust it equally, every one of them, if these boxes are running for long periods of time?
I'm not sure if I got the question right, but of course, one thing we have to do, no, at the beginning, if we start up a system, we have to load a short secret key on both sides in order to start the protocol and to authenticate the link. No?
So that's essentially session establishment.
Yeah.
How long can you trust that session establishment?
Well, then what happens, of course, what you do now, then you start the exchanging key.
Right.
And then whenever you exchange a key, you use this key, and part of it you use to authenticate the next session. So actually, I have to trust it only just at the very beginning, no? So if at the very beginning the eavesdropper cannot interfere immediately and get the key and then the future authentication key and make all the time a man-in-the-middle attack and so forth, I'm fine.
Thank you.
So I propose to thank Hugo first, and then before the coffee break, there will be a short presentation about the aerospace session.
Can we put on the short presentation that I prepared?
All right, everyone. So I prepared a quick presentation as sort of a introduction of what to expect in this afternoon's session for aerospace, but aware of time and aware as well that I'm the only one standing between you and coffee. I'm going to make it a one-slide teaser. This afternoon, there's an aerospace session taking place here in this room. I do invite you to come back. I'll be talking about the Airbus Quantum Computing Challenge. If you haven't heard about it or if you've heard only some info, I'll try and dig in a little bit more, give you as well some background. Why is Airbus doing this challenge in the first place? What are some of our motivations going into this? And give you some of the first statistics that we've been able to accumulate about interest participation. I won't be alone. There will also be a presentation by Tobias Stollenberg from the German Aerospace Agency, talking about some of his work, and a panel session as well with my colleague Paolo Bianco and Tobias, both answering questions from the moderator, and I think as well taking your questions. So please do come back this afternoon. Thanks.